All right. So we've looked at the simplest of metallic structures, albeit not very common. And so now we're going to look at the more common structures. And so these are BCC, FCC, and HCP. So let's start with the first one. So body-centered cubic is, again, a cubic structure. So that's our unit cell. The structure is a cube, right? So you can see the cube here, here, and you might be able to kind of see it here. BCC stands for body-centered cubic, and it is composed very much like the simple cubic, right? We have one atom on each of the corners, so one atom on each corner. But the difference is we have another equally sized sphere right in the middle of the cube. And so if we look at the space filling model, we see it here and here, right? So they're all the same size, so even though they're different colors here, they're the same. So they're all identical. And so with this one, if we look at the space filling, so this one and this one, hopefully it should be somewhat obvious that the diagonals in the cube, so from this back atom through the center sphere to the front, that's where the atoms are in contact, and any of the diagonals through the center. So I've showed this with the red lines here as well. That's where the atoms are in contact. So that's the close packing direction. And also, if we kind of consider this middle atom, all of the corner ones are touching it, right? And so those are the nearest neighbor, and therefore the coordination number is 8. And if we do the same calculation with atomic packing factor that we did in the previous module, you'll see that the atomic packing factor is higher, 0.68. So that means that roughly 68% of the volume here is occupied by atoms. So you can tell this is a bigger or a more dense structure than simple cubic, and therefore it's more favorable. So some examples that fall into this type of structure. This is a much more common structure. Chromium, tungsten, iron, that's probably going to be the big one that you see, is alpha iron. Iron can form into multiple different structures, but this is the common one. Tantalum and molybdenum. So and there's more too, but those are just a few examples. So basically we build upon this cubic, and then we place one in what we call the body-centered position, so right in the center of the cube. So that's BCC. So the next one, FCC, or face-centered cubic, is now, again, a cubic. We have atoms on the corners that you can see in all of these various diagrams of the same thing. But as the name implies, if we take a look at the face, so this top face, for example, of the cube, you'll see that there's an atom centered, and it's the same sized. So this is a good representation of that. You see that there's an atom right in the middle, along with all of the ones on the corners. So if we look at where things are touching, the direction of close packing, so again, not from the ball and stick model, but from these space filling models, you'll see that they're touching along the diagonals of the face, right? So this central atom is touching this, 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 and this, and you can kind of see it over here too. But the direction of close packing is along that direction. So if we go through this, then this means that one atom in this structure is coordinated or touching 12 others. So that's the coordination number. And we see that the atomic packing factor, if we do that calculation, then that atomic packing factor is 0.74. So higher than both of the other ones, simple cubic and BCC. So this has what we find out to be the highest packing. And so there's less empty space in the FCC structure. And we can do the same calculations, which it does down here that we did for simple. There ends up being 4 atoms per unit cell. So if we count the corners, that gives us that 1, right? 8 corners times 1/8. But then each face-centered atom is 1/2 of the sphere, and there's 6 faces, so 6 times 1/2, and that gets us up to 4 total. So that's kind of how we can look at the face-centered cubic structure. All right, so all the other ones so far have been cubic. They're based on a cube. Here, we have what's called hexagonal close-packed. So as you might infer from the name, it's going to be based on a hexagon. But it is what we would refer to as a close-packed structure. And what I mean by that is the atomic packing factor you see here is 0.74. So this ends up being the highest number that you can obtain if you have equally sized spheres. So this is why we call it a close-packed structure. And so basically how this is arranged is that we have a plane, so this bottom plane that you can see with A, C, D, B, and these other 3 atoms in a hexagonal form, which you also see up here. So these are all touching, right? So we see that, and then we see another, if we go up some unit, we see another plane, but it's shifted over. So it's shifted over where these atoms are in the empty spots. And then if we shift up again, it goes back to the original sequence that we see here in the base. So it's got these kind of parallel planes in a hexagonal form. And so hexagonal close-packed is also fairly common. Metals that have this form are cadmium, magnesium, titanium, so you might have heard of that one, and zinc. So again, atomic packing factor is the highest. Coordination is the same as well. It is also 12, like FCC. The main difference here is the shape, right? The shape is different than cubic. And since it is, we need more than one lattice parameter to find a hexagon. And so we actually use the lattice parameter A, which defines the base of the hexagon, and then C, which defines the height. And so that's what the C divided by A ratio is here. This is the ratio between A and C for this. So C is bigger than A in this case. And when we look at this hexagon, this unit cell, there's 6 atoms per unit cell, and the math here goes through how we arrive at 6. I just want to mention one thing. I didn't mention it before, but FCC, this is very common. I'm sure you know a lot of these types of metals: aluminum, copper, gold, lead, nickel, platinum, and silver. So there's lots of common metals that I think you've heard of with FCC. All right, with that in mind, I want to have us take a look at the periodic table. And so this is the periodic table of crystal structures for the different elements. And this is just reproduced from Wikipedia. So you can find this very easily. But if we look at all of these, this basically shows us that a majority of these are in fact the 3 that we've just talked about: BCC, FCC, and HCP. So you see here, lithium, the yellow color, is represented by BCC. So all of this column, again, similar valence structure and similar structure, are all BCC. Beryllium is HCP and is reddish in color, and so everywhere you see red is HCP. And then calcium is FCC, and represented by orange. And so if you look for those 3 colors, you see that a fair number of the metal side of the periodic table is one of those 3 structures. Obviously, there's a couple exceptions: mercury, indium, tin, gallium. But Those are all a little bit different. But for the most part, we can look at the structures of all of these by knowing the three that we've just talked about. So that's kind of the power of knowing these three structures.